Okay, so now we're going to get into the nitty-gritty of the subject outline for momentum in two dimensions, and we're going to look at Newton's second law and momentum. So before we get into momentum, we're just going to briefly revisit Newton's second law and particularly look at Newton's second law in two dimensions or in its vector form, which we may not have done before. So let's just consider a fairly simple situation here. We have a particle, and that particle could be like a tennis ball, and it's bouncing off a surface, which could be a wall. So we talk about surfaces and particles here in our intended student learning, so that's why I've used that language. So let's say, and this is what it wants us to do, you'll see in our intended student learning, we want to be able to calculate the force applied to the particle by the surface and the force applied to the surface by the particle, i.e. how much force does this ball exert on this wall and how much force does this wall exert on this ball. And I think most of you have probably all already got a rough idea, but let's just look at how we look at that and check we do have, I guess, a good theoretical understanding of that. So if we want to find out the force, we first need to work out the acceleration. If we want to work out the acceleration, the first thing we need to do is work out the change in velocity, because acceleration is equal to the change in velocity divided by the time. And in this case, the time is the time of our collision, which is the time of impact here, the time that the ball is actually in contact with the wall. So how do we work out the change in velocity? Well, hopefully by now we all remember that in this situation here, delta V, and remember we're dealing with vectors, equals Vf minus Vi, but these are vectors, so that is equal to Vf plus minus Vi, and minus Vi is parallel to that line but in the opposite direction. So that there is minus Vi, and then we use the tail to tip rule, and we can work out that change in velocity, hang on a second, that change in velocity, and I didn't draw that very well, but I just disguise it with the arrows, is equal to that. Now you'll note here the question says you only need to do this where the bouncing off a surface without a change of speed. So the magnitude of the initial velocity will always equal the final velocity. So the direction, when you add those two up, is always going to be perpendicularly away from the wall. So now that we know the change in velocity of the particle, or the ball hitting the wall, we can work out the acceleration using this formula here. Then, if we know the acceleration, we can use Newton's second law to work out the force that was applied. Now, it's a bit of a chicken and an egg. What comes first here? Does the ball apply a force on the wall, or does the wall apply a force on the ball first? I think the ball is moving along at constant speed. A force must act to cause it to accelerate. So a force must act because it changes direction, it's accelerating. So the wall exerts a force onto the ball, which is in a sense what we're working out here. And Newton's third law tells us for every action force there's an equal and opposite reaction force, so that the force that the wall applies on the ball will apply an equal force in the opposite direction on the wall. So just to put that in writing, from Newton's third law, the force the ball applies to the wall will be equal and opposite to the force the wall applies to the ball. So I'm hoping now that you've done a lot of stuff on 2 dimensions, you've done stuff previously on Newton's second law and third law, both through middle school year 10 and year 11, that is a fairly simple concept to understand. I'm not going to bother going through a worked example for that, because I think all of the skills that you need, obviously you're going to need to use some trigonometry here or a vector diagram to work out delta V. That's all skills that you should be reasonably familiar with. If you're not familiar with them yet, that's okay. By all means, sing out and ask questions. But I don't want to make these videos unnecessarily long by going through things that I think most people have got a reasonably good idea of now. So now we're going to get into the momentum part of Newton's second law. So we're going to look at Newton's second law in terms of momentum. We're going to start out by deriving this relationship here that relates force and momentum. So Newton's second law, previously we've thought of as force equals mass times acceleration. So we're going to show that we can now think of Newton's second law not only as mass times acceleration, but also as momentum divided by time. And we actually need to be able to derive this relationship. So this is going to be what I call a need to know derivation. So, let's make a start. So we know that from Newton's second law, force equals mass times acceleration. But the acceleration can be given by, if we go off our formula sheet, delta V on delta T, which is equal to Vf, the final velocity, minus the initial velocity divided by time. And we're going to substitute this expression here for acceleration back into this equation here. So we're going to substitute that into there, and we're going to get that force equals mass times Vf minus Vi divided by time. So we've just written out this expression here a different way by substituting in the value for acceleration. If we expand that out, we get that force equals mvf. So mass times the final velocity minus mass times the initial velocity, and that is all divided by time. And I should have used here delta t. It's the change in time, which is the time of impact or the time the two bodies are in contact during the collision. Now, from the earlier introduction to momentum video, hopefully you remember that momentum is given by mass times velocity. So by simplifying this, we can say force is equal to the final momentum minus the initial momentum divided by the change in time, or force is equal to the change in momentum, Pf minus Pi divided by the change in time. So we've derived this expression here, down here. So that's the derivation. We can now use this formula here to solve a very similar problem to we looked at on the previous slide. In the previous slide, where we have a particle, which might be a ball hitting a surface, which might be a wall. But rather than considering the change in velocity and then Newton's second law to work out the force, we can do it directly from momentum. We sort of save ourselves a step. So in a very similar fashion to before, if we want to calculate the change in momentum, is equal to Pf minus Pi. So we're doing momentum, not velocity. That's the only change. Change in momentum is equal to Pf plus minus Pi. So we've got Pi there. So that becomes minus Pi. And if we do the tailed tip rule, we get delta P there. And we can solve that basically using trig, or if we want, a scale diagram. Now, that's very similar to the problem on the previous slide, which is very similar to the sort of two-dimensional vector problems we solved when we started out doing projectile motion. So I'm not going to go through a detailed example of that. Obviously, if you have any troubles with that or you're not sure on anything there, please sing out and ask me. Thanks.